Alright, tomorrow we have the electrodynamics exam, so we should probably go through all the topics. And it's definitely complicated here, but just give me 1 second here. The idea is we have vector calculus and stuff like that up at the top. But the most important things for this top section is going to be the delta function, which is this Kronecker delta. It's kind of like the identity function. And we already kind of went over most of these things. So should realize that, yeah, we could take a little derivative here by doing a dot product. dj times xk. Let me get this jk thing. I guess that makes sense because we're just doing this. Um, so anyway, let's also look at the Levi-Civita, which is this. It's important to know how to essentially prove this formula. Say you plug in E, and then ijk, and then delta jk. If you plug in a 1, then you see that you have all these other pairs that show up, and all of them cancel except for these two. And so, that sort of proves the Levi-Civita tensor situation. Now, here's another interesting equation. They both equal 0. So divergence after taking the curl, or the curl of a scalar. This is a derivative of the scalar. So, yeah, first section is a little bit crazy. In the next section, we deal with Poisson equation, Laplace equation, and just realize that the total charge is going to be the bound charge and the free charge together. So this is all about trying to solve potentials and electric fields, but we can use the brute force method, which is just like putting in integrals and trying to solve that. Or we can use other tricks, like the image charges. Images automatically satisfy the Laplace equation, which is cool. So, you just have the infinite image charges. The other day we figured out that was plus or minus 2 nL. Um, Here we have the dipole moment, QL. The distance is always going to be x squared plus y squared z minus zn. And of course, we could also find it in a sphere, which is going to be this one right here. This is a sphere with image charges. So you have the q is equal to negative q r over d, z is equal to the center minus the r squared over d, and yeah, so this is how we would always set up the image charge voltage. Now, for cylinders and spheres, if we're trying to solve this Laplace equation here, we basically have to jump to these two solutions automatically, because in general, you're going to have azimuth symmetry, so m equals 0 or v equals vr. Basically, you can see how it doesn't matter where you are in terms of the um, uh, this one right here, azimuth 0 over 2 pi. Okay, and this one here also in the same way. If you go around this uh, radius here, or the circumference, nothing changes. You have symmetry, so everything's in the radial direction. So in general, you kind of want to jump over to something like this. So this one assumes you have R phi. This one assumes you have, oh, I think here we have the, this is azimuthal symmetry, and here we have Z symmetry. Yeah, so that's kind of the main difference. So here you have Z symmetry, and here you have azimuth symmetry. So you can see that the symmetry is removed. Anyway, here you get Cauchy-Euler times a simple harmonic motion, and you kind of have to infer what these m's are based off the shape of the boundary conditions. And here you have Cauchy-Euler times the polynomials. Cauchy. Cauchy-Euler. Alright, remember that we're going towards the r equals 0. The BL term goes to 0, and if we go to r to infinity, the AL term goes to 0. Now, if there's a charge at the origin, then we have to keep the monopole regardless. So that's immediately jammed into our solution. Um, Here's another way to sort of jump to a quick solution for voltage. You consider the monopole, dipole, quadrupole, or higher terms if you want, using the sum. And then this is kind of for the R and the far field. But so here are the three different integrals. Here's just the regular charge integral for this. This one's the dipole integral. It contains the C. This one is the quadrupole integral, R squared. So you can solve these integrals, and then you can sort of get an answer for that. Here's some equations that help when we're dealing with dipoles. Again, we have to do these boundary conditions. There's three types. You got the limits, r to 0 and r to infinity. There could also be a constant field of infinity, so like the voltage is equal to the integral of the electric field out there. You could have surface boundaries, so like the voltages have to equal um, grounded surfaces. You have to zero the potential there. Well, we could also think about the flux. So the Maxwell boundary. That would be like E out minus E in, and then you have to take the derivative of the voltages. The tangential one has a continuity, this one has a discontinuity. What that means is the continuity means you just have equal, and the discontinuity means that there's a that it equals the epsilon naught over the there's a surface charge there. Um, so we've discussed a lot of this already, though. Keeping in mind, we always have to deal with like either the Cartesian coordinates, or the cylindrical coordinates, or the spherical coordinates. And so we have all these different solutions to like the Laplace differential equations based on the coordinate system. In the Cartesian, we tend to get regular old simple harmonic motion. It's more interesting when you go to the cylindrical, you get the Bessel functions. In the spherical, you get the Cauchy-Euler Legendre. This is kind of the one we usually do because I guess it's a little bit more interesting. Here are the spherical harmonics and the Legendre polynomials. So there's a lot of stuff about all this. And the most important part is to just remember that 1 is L equals 0, cosine theta is L equals 1, and then there's this um, two ways to write this one. 3 over 2 cosine squared minus a half, or 3 over 4 cosine 2 theta plus a quarter. This is the L equals 2 condition. Um, this is an interesting section. This is kind of new stuff. Let's consider these sheets. So a sheet of charge here, on top of it, we would have the positive sigma over 2 epsilon. On the bottom side, we have the negative sigma over 2 epsilon. And if we have a little pillbox flux, we can count it like, well, there's two surfaces here that are shooting out. And I do believe that we just sum them. So we have 2a sigma a over epsilon naught. And the Maxwell surface is basically saying that you would take the top side minus the bottom side. And, well, if you do that, then you're going to get sigma over epsilon naught. So you get that Maxwell surface there. Now let's say you have a sheet of potential, not a sheet of charge. It's not that interesting when you have one, but if you have two, it's a little more interesting because these are z boundaries. So it's kind of forces dv dx equals 0 and dv dy equals 0. So this essentially gives you z dependence on voltage. Let's take a look at throwing in one that's v equals 0, one that has v naught. There's a cool trick called the odd extension for Dirichlet boundaries that we can actually reflect this over the 0 axis there. This is the image that's negative v naught. So that way this cancels out over here in the middle. And then we can go ahead and put in charges, positive and negative charges, so that it'll allow us to sort of calculate what the electric field is in these regions. Of course, we have to combine them because now we're superimposing them. Here we are subtracting them because we only have one surface. There's also the odd extension for Neumann boundaries, but this one's a little bit less used. I mean, all this Dirichlet and Neumann stuff means is that Dirichlet says you have a fixed value at R, so some constant or maybe some kr, some sort of number that you can rely on, a fixed value there. The Neumann is just a fixed derivative instead. So these are just like this is the common boundary condition that we're all familiar with, the Dirichlet boundary condition. And the Neumann boundary condition is we have to fix the derivative instead of the position. So that's that. A little bit more reflection stuff. Here's a 2D Laplace. We have two variables, x and y, and the idea is that we have to have one that does oscillations and one that does exponentials. So here are the two equations. Notice how this one is the oscillations, and this one is the quotient sinh, which are exponentials. It's a little bit weird. We also have reflection symmetry. So if we see that we can reflect stuff symmetrically across the z-axis, for example. Then we have even L's. The antisymmetric one, if it becomes negative across the axis, then we have odd L's. Um, well, there's so much stuff to do in this electromagnetism thing. I think so far we've covered a lot of it. Let's look at this potential difference stuff here. Um, if the voltage is pointing inwards, then the electric field points outwards. So you would have less voltage here, more voltage here, means that your electric field points outwards. So you get pluses in the center, minuses towards the outside. Realize that VR minus VA is equal to the negative integral of the electric field. Alright, so I guess we'll get into just the polarization and displacement stuff here. It's pretty confusing, but I guess we have these equations, which we tend to need. Bound charges for the volume and the surface, and also the free charges for the volume and the surface. We can consider the displacement normal continuity here, and also Gauss's law for displacement. This is the free charge. Here's the energy. We have the linear dielectrics as well. Just a couple of equations added there, which gives us all these weird things about permittivity. And then the image reflection for something with permittivity. We have to do this kind of stuff where epsilon, if we're going from epsilon to epsilon naught and reflecting it, then we have to use this alpha epsilon minus epsilon naught over epsilon plus epsilon naught. And the Qn becomes Q times negative alpha to the power of n. We can jam this together and come up with some kind of a solution. Anyway, all this stuff is just very messy, but I guess that's just kind of how electromagnetism is. Uniqueness is one solution, always is always the same solution if it works. All right, well, this is a pretty big mess. Not a lot of it makes sense, but hopefully this was a little bit better than nothing. You all have a awesome night.